Okay, for this screencast, we are going to do a PID controller. And so what I'm going to do is I'm just going to set up the basic equations of motion. And so what I want to do is I want to set these equations up, and I really want you guys to take a look at them and understand that literally this code is the same for every single set of equations of motion. The only difference is going to be the part at the end, which is x double dot. And so right now I'm just going to set x double dot equals 0. So this is the only thing that will change. And this is really for second order systems. Okay? So then let's see, z dot is x dot and x double dot. Okay, I think that's it for the derivatives routine. So then we need z initial, z int, and z initial. So I'm just going to say 0 initial conditions. Let's actually make it like 3. It doesn't really matter what it is, but we'll make the initial conditions 3. And then we got to do t out, x out, or z out, sorry, is OD 45 at derivatives. Let's see, t span, and then z initial. And then t span, I'm going to say go from 0 to increments of 0.01. I don't know, 10 seconds. That's probably fine. And then plot t out. And then I want x out, which is z out of all comma 1. And then I'm just going to plot x out. And then you need to put labels. But this, okay, let me make sure this code runs. So let me type in PID, and let's see what I get. Yeah, okay, it worked. So this is x and time. Okay, and you should label your axes and everything like that, but I'm just being lazy. This code is always the same. Okay, so whenever you start making your code and you're trying to copy code from other places, try to get this to work first, because this will never change. It will always look like this. Okay, what changes is, let's say your system looks like this, and it says x double dot plus 5 times x dot plus 3 times x equals, and I'm just going to put u of t, or f, where f is the input forcing function. Okay, this is where this changes. All you need to do is you just need to put everything on the right hand side, and then that's it. The only thing that you need to do, though, is you need to make sure that f is defined. So for now, I'm just going to say that, you know, our input f is 0, and we'll change that when we start doing the PID controller. But anyway, if we run the PID control, the system now, where's my plot? There it is. So is my system overdamped? What are roots 1, 5, 3? Come on. Yeah, okay. I have an overdamped root. So how do I change this? If I make this like 2, is that underdamped? Oh, and I need to put a close all. That's why. There we go. All right, sweet. My system's a little underdamped, and so it oscillates now. That's what I wanted. Okay, so again, take a good look at this code. All right, initial conditions, span of my time 0 to 10, my derivatives call, my extraction of my state, my plotting, my derivatives function header, x and x dot, f is my input, and x double dot over here is this equation, the equations of motion inverted, or just everything put to the other side, and then z dot. Okay, this code will never change unless your equations of motion change. Okay, all right, so let's do some PID control. So right now our system is at 3 and it comes back to 0. I want it to go to 10. Okay, so for now we're going to just do proportional control. Okay, so proportional control is kp times e. Okay, what's e? Well, e is x. If you look at the control block diagram, it's x command minus x. Well, x is already defined, so we have that. X command, I need it. So what is my x command? I'm going to say it's 10. And then I'm going to run this. Oh, it's not going to work because I need kp. I'm going to try kp equals 5. Why? Just because guess and check is nice. Okay? There's my system. It shoots up. I have a bunch of steady state error. I could make kp 50. Try it again. And now my system oscillates like crazy, but my steady state error went down. So if you notice, I have more overshoot and more oscillations than I did before. if I do KP5 and I run it again, here I have not as much overshoot and not as many oscillations, but I have more steady state error. So I'm going to leave it at 50 so that I have less steady state error, but I have a ton of overshoot. In order to get rid of overshoot so that it smooths out, you need to add derivative control. Okay? So then you need, instead of F is this KP times E, you do KD times E dot. So what is E dot? Well, if you look up here and just take a derivative, you get XC dot minus X dot. Again, X dot is already defined, and then it's pretty simple because XC dot is a constant, so derivative of a constant is just 0. And then KD, I'm going to just call it 25. Why? Because KP divided by 2 sounds good. All right, I'm going to run this, and look at that. Oh, you can't see it. There you go. Look at that. Oh, of course, Octave is not so good. Okay, there you go. Boom. Now it's super smooth. I still have that steady state error. Okay, so I can play around with these KPs and KDs all I want, but I'm never going to get rid of the steady state error. So what I need is integral gain. Okay, so the problem with integral gain is you need to do Ki times the integral of E. So I'm going to call it E int for integral. Okay, so Ki, I'm just going to make it 10. But how do you get E int? Well, E int is difficult, and I could do this derivation on the board, but I don't have a board right now. So basically what happens is if you say that E int is the integral of E, right? Integral of E, then that means that E int dot is just E, right? So then what I'm going to do is I'm actually going to add a state. So I'm going to put E int is Z of 3. And then I'm down here, I'm going to have x double dot, or x dot, x double dot, I'm going to have E int dot. Okay, so how do I get E int dot? Well, I just told you, E int dot is E. And where's E? E is defined up here. So I already have E. Then what I need is I need to make 3 initial conditions. So the initial x is 3, the initial x dot is 0, the initial E int is 0. And then I run that, and boom, integral gain. No steady state error. Done. Okay? This is 40 lines of code. It is very simple, okay? You have this is always the same. You have x dot, x dot, E int. Those are your initial conditions. You have your OD45 function called. You have your x out, your plotting. You extract all your states. Again, x dot, E int. You have your proportional part, your derivative part, your integral part. You have your derivative of your integral part. You have your PID controller, I guess I could put it PI, KI times E int plus, and then put this over here, P times I times D, right? The proportional integral part. You have your derivatives routine, or your equations of motion, which is always the same, and then now Z dot, which is the derivative of x dot, the derivative of x dot, which is x double dot, and the derivative of E int, which is E int dot, and like I said, E int is just E. And then you can play around with those gains all you want, and you get your system there. So it started off at 3, and it goes to 10. You can change your initial conditions all you want. You could make this -2 and this 5, and you could run that, and it would do some weird stuff in the beginning, but it still gets to 10. So your PID controller is working. Let's make this -5 just so it does something weird, just because. So now it'll probably go down a little bit. Nah, it still didn't do really much. It still didn't do much. Yeah, it went down a little bit. Oop. All right, I think I'm just wasting time at this point. All right, good luck. I hope you understand this video now, or PID control now. Good luck.